The most common method of representing the structure of a hydrocarbon such as alkanes is structure formula. Now, structure formulas are useful for showing the connectivity of atoms in a molecule. For example, if I draw the structural formula of ethane, so we know that ethane has two carbons and each carbon is connected to uh, three hydrogens. So this would be a structure formula. However, structure formulas do not show the actual three-dimensional shape of the molecule. In this section, we will take a closer look at the three-dimensional structure of alkanes. The three-dimensional structure of a molecule is called stereochemistry. In this chapter, we will understand the rotation around the carbon-carbon single bond. However, in next chapter, we will learn more about other aspects of stereochemistry. We must remember that the rotation occurs around the carbon-carbon single bond. So it means that this bond can freely rotate. So thus, when uh, there is a free rotation around this bond, the hydrogens on one carbon adopt different orientation relative to the hydrogen of the other carbon. So these different arrangements are known as conformations. So hence we can define conformation as any three-dimensional arrangement of atoms in a molecule that results from rotation about a single bond. So we have learned that the alkane molecules can adopt different conformations by rotating around the carbon-carbon single bond. So let me take an example of ethane molecule one more time. So ethane has two carbons and they are linked by a carbon-carbon single bond, and each one is connected to uh, hydrogen. So I will use different colors to represent the hydrogens connected to two different carbons. Now, because we stated that there can be or there is a free rotation about the carbon-carbon single bond, so it means this molecule can rotate freely. So when this molecule rotates freely, so this hydrogen, which is right behind the red hydrogen, the blue hydrogen will move to the right hand side slightly. So depending on how many degrees it's rotating, the geometry will be slightly different. For example, if it rotates slightly, so it will adopt a geometry something similar to this one. So now we can see that the blue hydrogen is not right behind the red hydrogen. So if it continues further down, there is no limit by how much degree it can rotate because it's a free rotation. So let's imagine it rotates more, and then eventually it adopts a conformation where the hydrogen is exactly opposite to the other one. I'm not going to draw the other hydrogens. Sorry. Now this geometry please remember that we are only paying attention to these two hydrogens. As you can see, the blue hydrogen is moving as we are rotating further. So the geometry which is shown here, in this case the red hydrogen and the blue hydrogens, they are exactly opposite to each other and there is nothing. So this geometry is known as, or this conformation is known as staggered conformation. So a staggered conformation is that conformation in which the hydrogens on one carbon are as far apart from the other hydrogens to the hydrogens connected to the other carbon. So this geometry is a more stable geometry because it minimizes the repulsions between caused by the hydrogens which are in the vicinity of each other. In the next slide, we will see that the geometry shown here on the left hand side, where the hydrogens on one carbon are exactly at the same plane to the other one. So this kind of arrangement causes steric repulsions, and these steric repulsions cause strain. We will learn more about strain in a little while later, but remember, when hydrogens are exactly behind each other, they cause strain, and the strain means the energy of the system or molecule in this conformation is high. And this conformation is known as eclipsed conformation, and we will talk more about eclipsed conformation in next slide, but let's focus on the staggered conformation. So staggered conformation is the most stable conformation of alkane because the hydrogens are as far apart as possible. There is a better way of visualizing the conformations of alkanes, and that method to visualize is known as Newman projection. In Newman projection, we visualize a molecule from the side. So imagine that a person is looking from this angle. So this is our eye. So we are looking from this angle. So when we look from this angle, we will look at this carbon. So I'm gonna call this as carbon number 1, and the other carbon will be away from your eye, so I'm gonna call that carbon number 2. So similarly, the blue spheres represent hydrogen, so all the hydrogens which are connected to carbon number 1, I'm gonna call them hydrogen 1s, and all the hydrogens which are connected to carbon number 2, they are 2 hydrogens. Okay, so if a person is looking from the side, all that person gonna see is this arrangement. So where this one will carbon number 1 and carbon number 2 is behind, and number 1 gonna cover up the carbon number 2. So that the little smudge is carbon number 2. We can't really see carbon number 2. Similarly, the hydrogens which are connected to the number 1 will be visible. For example, this is hydrogen number 1, hydrogen number 1. So these 3 hydrogens are directly connected to carbon number 1. So the other hydrogens are connected to the carbon number 2, which is in the back. So because hydrogens are protruding out, so we will see them. And now you can see that number 2 hydrogens are exactly in the middle of number 1 hydrogen. So that's the farthest distance possible. So in Newman projection, we show our molecule in this format, where a big sphere represents the carbon. The other sphere is behind, so we can't really see them. So these hydrogens which are connected to the front sphere, I'm going to call them 1, 1, and 1. So these are the hydrogens which are connected to the carbon atom in the front. The other carbon atom which is in the back, and we can't see it, so the other two hydrogens are the other three hydrogens, we can still see it, and we're gonna call them a hydrogen number 2. So this kind of arrangement is known as Newman projection. Eclipse conformation is a conformation about carbon-carbon single bond in which the atoms or groups of atoms on one carbon are as close as possible to the atoms or groups of atoms on the adjacent carbon. So the ball and stick model and Newman projection of eclipse conformation of ethane is shown here. So we can see this is 1, 1, 1, and 1. That's 2, 2, 2, and 2. So now we can see clearly that the 1 and 2 are as close as possible. So this is the front view. If we visualize it from this side, then we will look it this way. So now we can see number 1, 1, and 1, and 1, and those are. So we can see in eclipse conformation, the hydrogens connected to the one carbon are right uh, uh, ahead of hydrogen connected to number 2 carbon. So the distance is the smallest, and this represents the Newman projection of eclipse conformation. In eclipse conformation, because of the steric repulsions between the hydrogen atom, there is a strain. So the atoms don't like to be that close to each other. So that's why eclipse conformation is relatively higher in energy. Molecules don't want to be in eclipse conformation because that puts a strain in their structure. Now, in order to go from eclipsed to staggered, uh, the carbon-carbon single bond needs to rotate, and it needs to go this way. So how many degrees does it need to rotate? So we can easily find out, because in order to go from eclipsed to staggered, the rear hydrogen need to go right in the middle. So this angle by which it needs to rotate is 60 degree. So going from eclipsed to staggered, which means least stable to most stable, the carbon-carbon single bond must rotate by 60 degree. If the staggered conformation further rotates by more another 60 degree, it will go back to eclipse. So it means for every 60 degree rotation, the conformation will go from eclipse to staggered. Further 60 degree rotation means it will go back to eclipsed. And the cycle continues. In principle, there can be infinite number of conformations possible in ethane molecule. For example, if I draw this molecule in such a way that the hydrogens are farthest away from each other as shown here. So this geometry or this conformation shown here is the most stable conformation as discussed earlier, and this is staggered conformation. Now if the carbon-carbon single bond rotates, the molecule will go from the most stable to relatively unstable position, because any rotation will cause the hydrogen molecules to come closer to each other. So, and we also discussed in previous slide that a 60 degree rotation will make the staggered conformation into eclipsed conformation. So in other words, if we rotate by 60 degree, our molecule will adopt eclipse conformation. And we also discussed that because of uh, the steric hindrances, the eclipse conformation is not stable, and it is higher in energy because it's unstable. So because of this, the rotation around the carbon-carbon single bond is not free because molecule is going from stable to unstable. So it needs some energy. And any rotation around the carbon-carbon single bond, it brings a strain to the molecule, and this strain is known as torsional strain. One way of understanding the higher energy content of eclipse structure is by taking an example of a system which goes from a relaxed state um, to uh, strained state. For example, bow and arrow. So if we take an example of a bow, and this is the relaxed state, and if we want to shoot the bow, we have to stretch the string of the bow, something like that, and we need to put an arrow there. So now there is a strain. This strain makes the bow to adopt a geometry which is under strain, and hence bow will have higher energy. And when the bow goes from higher energy state to the stable state, it will transfer that energy and then it will shoot the arrow. Similar thing happens in going from staggered to eclipsed. So from going from staggered to eclipse, the molecule uh, comes under a strain, and that strain makes the molecule to have higher energy. Although I'm trying to make it sound like there's a lot of energy, but in actual practice, this is the energy required to go from staggered to eclipse is not that high. It needs only 12.6 kilojoules per mole. This is extremely a small amount of energy, and this much energy is available at room temperature also, freely available. The room temperature is enough to provide this much energy. So in actual practice, ethane molecule go from eclipsed to staggered all the time because it doesn't even it doesn't require that much energy. This strain is also known as eclipsed interaction strain. The definition of torsional strain is the strain that arises when non-bonded atoms separated by 3 bonds are forced to form a staggered conformation to an eclipsed conformation. So what do I mean by that? So the meaning is that the non-bonded atom, so this hydrogen and this hydrogen, so they are non-bonded to each other. Yes, they are bonded to carbon, but they are not bonded to each other. And now they are separated by 3 bonds. That's 1 bond, 2 bond, and 3 bond. And when we force these non-bonded hydrogen atoms separated by 3 bonds to go from staggered to eclipse, as we did here, so that strain is known as torsional strain. In the discussion of conformation of alkanes, it's important to define and understand dihedral angle. Dihedral angle is denoted by a Greek letter theta, as represented here, and it is defined as the angle created by two intersecting planes. For example, if we consider an ethane molecule, as shown here, and it's in the staggered conformation, then the dihedral angle of this molecule will be the angle or the plane passing through hydrogen, this one carbon, and the other carbon, which is this one. So this would be the dihedral plane of this carbon and hydrogen, the one in the front. Similarly, if we want to define the dihedral plane for this hydrogen, then it must be a plane passing through this hydrogen as shown in the blue line, this carbon and the other carbon. So that would be the dihedral plane of this molecule. So each dihedral plane is defined by 3 atoms. Examples of dihedral planes in ethane, in eclipsed conformation as well as staggered conformations are shown here. And we can see that in eclipsed conformation, the dihedral plane from the back CH and in the front CH, they are aligned at the same axis. So both planes are exactly in the same orientation. So in this orientation, or in this case, there is no angle difference between two planes. So in this conformation state, the dihedral angle is said to be 0. Now, if our molecule is in staggered conformation, now we can say that the front CH plane and the rear CH carbon hydrogen bond plane, they are not aligned with each other. They are separated by 60 degrees. So in staggered conformation, this dihedral angle is 60 degrees. The relationship between dihedral angle and the energy of ethane molecule is shown in this figure. So we learned in previous slide that when dihedral angle is 60 degree, ethane molecule is in eclipsed conformation. And we also know that eclipsed conformation is relatively high in energy. So at 0 degree angle, our molecule will be in eclipsed conformation. So eclipse means the rear hydrogens, let me draw the rear hydrogens with different color, are exactly behind the front hydrogen. So this is eclipsed conformation. So as the carbon-carbon bond rotates, so these hydrogens move away from each other. So red and blue hydrogens move away from each other. So that releases the torsional strain. And as it releases the torsional strain, the energy of the system starts going down. And so energy is going down. And once the dihedral angles are at 60 degrees from each other, at that point, the molecule adopts a staggered conformation as shown here. And staggered conformation is a conformation where the CH bonds are maximum away from each other. So the minimum torsional strain, or we can say zero torsional strain. So in this position, the energy will be the least. And the difference between the highest energy and the lowest energy is equals to 12.6 kilojoules per mole. Now, once the molecule is at 60 degree and we rotate it further, now the molecule starts going from stable to unstable position. So this will increase the torsional strain. So the energy of the molecule will start moving up, and eventually it will go back up to eclipse position. So that will happen at 120 degree angle. Remember, each 60 degree rotation will change the molecule from staggered to eclipsed and eclipsed to staggered. So back up again the energy will be maximum. The further rotation will bring the molecule back to staggered. That will happen at 180 degree, and then this process will continue, and we can draw this energy diagram up to infinite number of degree rotation, but we will stop at 360 degree. In the beginning of discussion of this section, I mentioned that torsional strain arises because the hydrogen nuclei creates steric repulsions. And this was the original idea which was proposed by many researchers. However, in recent years, there has been a lot of disagreement over the actual origin of the torsional strain. Originally, it was uh, it was assumed that it wasn't assumed, it was proposed that because in eclipse conformation, hydrogen nuclei are only separated by a distance of 235 picometer, and in staggered conformation, the hydrogen nuclei are separated by 255 picometer. So because they are closer to each other, so that will create some kind of a strain or repulsion. So that was reasonable idea. So this idea was further supported by the fact that it was proposed that there might be repulsions between the electron clouds of this carbon hydrogen bond with the electron cloud of this carbon hydrogen bond, and these repulsions would make the molecules more unstable. And because carbon hydrogen bonds are further separated from each other in staggered, so repulsions will not exist, hence uh, it will be more stable. So all of these point to the fact that the steric repulsions are responsible for the strain. However, modern advances in computer science and other technology, we have now uh, calculated from theoretical molecular orbital calculations that the energy difference between the conformational extremes arise not because of destabilization of eclipse conformation, but it is rather from stabilization of staggered conformation. So in other words, the computer simulations have suggested that eclipse is not unstable at all. It's rather opposite, which means that staggered is more stable than the eclipse. This stabilization of staggered conformation arises because of a small donor-acceptor interaction. The meaning of donor-acceptor interaction is donation of electron density from a filled orbital into an empty acceptor orbital. So this donor-acceptor interaction occurs between a filled carbon-hydrogen bonding molecular orbital of one carbon and empty carbon-hydrogen antibonding molecular orbital on the adjacent carbon with which it is aligned. And this donation is only possible when the molecule is in staggered conformation. So if molecule goes from staggered to eclipse, this additional stabilization because of donor acceptor interaction is lost, hence eclipsed is less stable. So regardless of what's the reason, the fact remains that eclipsed ethane is higher in energy than staggered ethane. The reason of this energy difference is still a subject of study among scientists. So at this point, we only need to remember is that eclipsed is relatively unstable than the staggered conformation in case of ethane. In case of conformations of ethane, uh, the increase in energy of eclipsed orientation or eclipse conformation depends only on torsional strain. However, when we look at the relative stabilities of various conformations of larger molecules such as butane, uh, we encounter many additional kind of strains in addition to torsional strain. The presence of all those various kinds of strains will increase the energy of certain conformations. So the increase in energy resulting from the distortion of bond angles and bond lengths uh, is known as strain energy. In case of butane, in addition to torsional strain, we encounter two other kinds or other types of strain. So the first one is angle strain and the second one is steric strain. Steric strain is also known as non-bonded interaction strain. Steric strain results when non-bonded atoms separated by four or more bonds are forced closer to each other than their atomic radii allows them to be. When that happens, these atoms are forced to smash into each other. So what do I mean by that? So let's take an example of butane. So in case of butane, the structure formula is this. It doesn't really tell us anything about the stability or conformation of strain. However, in some conformations, butane molecule can adopt this geometry. So when that happens, uh, the hydrogen atom connected to the first carbon and fourth carbon, so this is number one carbon, that's number four. So one of the hydrogen on first carbon here and the hydrogen connected to the fourth carbon, let me use different color here. So they come too close to each other, and this uh, the distance between these two hydrogens is less than their atomic radii, so they are forced to smash into each other. So that results in a lot of strain in the molecule in this conformation. This is one of the conformation. And this strain will result in increase in the energy of this entire molecule. And this kind of strain is known as steric strain or a non-bonded interaction strain, or it's also known as van der Waals strain. And remember, these two hydrogens, the one which is connected to one hydrogen, number one carbon, the other one is connected to number four carbon, they are separated by four or more bonds. Angle strain results when a bond angle in a molecule is either expanded or compressed compared to its optimum value. Now we know that in alkane, all carbons have sp3 hybridization, and in sp3 hybridization, the optimum angle is 109.5 degrees. However, in certain cases, the molecule is forced to adopt a geometry in which the angle is not 109.5 degrees. For example, in case of a cyclic molecule such as a cyclopropane, the angle between carbon-carbon is 60 degree. It is almost half the value of optimum angle value. So this will create a huge angle strain. Similarly, in case of cyclobutane, the angle is 90 degree. It's still better than cyclopropane, but still a lot of angle strain. And in many cases, the angle may have a higher than 109.5 degree value. So in that case also, we will observe angle strain. So all these angle strains will increase the energy of the system and they will contribute to the strain energy. So strain energy is the combined sum of all the energy because of steric strain, angle strain, or torsional strain. Now let's take a look at conformation of butane. In case of butane, we visualize through the carbon-carbon bond passing through carbon number 2 and carbon number 3. Let's pay attention to the ball and stick model of a butane shown here. So this is carbon number 1, 2, 3, and 4. So for these conformations, we visualize through the bond passing through carbon number 2 and carbon number 3. And as we understand, carbon carbon bonds can freely rotate. This conformation or this arrangement, if we look from carbon 2, so it will appear that carbon 2 is here and 2 hydrogens are connected to carbon number 2, so these two, and then carbon 3 is right behind it, so that's carbon number 3. Now carbon number 1 is connected here, so this will be carbon number 1, and carbon number 4 is connected to carbon 3, which is here. The Newman projection of this arrangement is shown here. So this is Newman projection of butane. So again, this is carbon number 1 and carbon number 2 is the sphere shown here. So carbon 1 is connected to carbon 2 and then 2 hydrogens. Carbon 3 is right behind the sphere and this carbon 4 is connected to carbon 3 and those 2 hydrogens. In this arrangement, the bulkier units such as methyl groups are farthest away from each other, and this is the most stable conformation of butane, and this conformation is analogous to the staggered conformation of ethane. Please recall that in staggered conformation of ethane we also had a similar arrangement. However, we don't call this staggered because we don't have the same atoms connected to. We have hydrogens and methyl groups. So this conformation of butane is known as anti-conformation. So anti-conformation is a conformation about a single bond in which the groups, the methyl groups in case of butane, lie at a dihedral angle of 180 degree. 180 degree means they are exactly opposite to each other. Okay. So if I have to show the anti-conformation of butane, so this would be the anti-conformation of butane. So in this conformation, the bulky groups are the dihedral angles of bulky groups. So this one and this one, they are exactly 180 degree away from each other. So this is the most stable conformation of butane. As discussed earlier, that in case of butane, angle strain and steric strain also contribute along with the torsional strain to conformations of butane. So the total of all types of strains can be calculated by molecular mechanics programs. Angles and bond lengths are chosen in an iterative procedure so that the optimum geometry with the lowest possible total energy is calculated. Such kind of calculations are performed by computer programs such as Chem 3D and Spartan. Molecular mechanics calculations carried out with these or other programs can determine the lowest energy arrangement of molecules in a given conformation of a molecule. So this process is known as energy minimization, and the computed minimized energy conformation in case of butane is represented here. So this is a butane molecule in anti-conformation. it has been found with all these energy minimization calculations that in anti-conformation, the angle between carbon-carbon and 3 carbon bonds, so this angle is 111.9 and not 109.5 degrees. So we know that it's sp3 hybridization state, and this angle is supposed to be 109.5, but when it's 109.5, so these two groups become too close, which may result in some strain. So hence the angle is slightly larger to avoid the steric repulsion. But this larger angle will create some angle strain. So it's always about positives and negatives. So because this angle strain probably is smaller than the steric strain, so the molecule prefers to have angle strain. Similarly, the carbon, hydrogen, and hydrogen angles, so these angles are found to be anywhere between 107.4 to 107.9. Although this is the most stable system, and it doesn't have any torsional strain because the larger groups are farthest away from each other, but it still has some angle strain. And the calculated strain is about 9.2 kilojoules per mole. It's not a lot, but still there is some strain. Now let's consider the eclipse conformation of butane. The Newman projection of eclipse conformation of butane can be drawn this way. So the circle represents carbon number 2, and carbon number 1 is connected here as CH3, and carbon 3 is right behind carbon number 2, and the blue hydrogens and blue methyl group represents the methyl group and hydrogen connected to carbon number 3. As we can imagine that the large and bulky methyl group with zero dihedral angle between them will result in a lot of steric strain, and that is true. This molecule indeed has a lot of steric strain. A computer-generated models of butane molecules in eclipse conformations are shown here. Figure A, or the molecule in figure A, represents a ball and stick model in which no energy minimization calculations has been performed yet. So in this case, if we assume that the carbon bond angle at this position is same as the anti conformation, and we remember that in anti conformation it was 111. So if we keep it same way, by keeping this angle and this geometry, the hydrogens which are connected to number 1 carbon and number 4 carbon, they are only 178 picometers apart. This is too small. This is even smaller than the combined sum of atomic radii of these two hydrogen atoms. Although it's represented farther away, but 178 picometer means that these two hydrogens are now touching each other or even pushing each other. They are so close. So therefore, this geometry of eclipse conformation is highly unstable, so it will be highly unlikely. So instead of staying or keeping the angles close to the ideal value of 109, the molecule will adopt a geometry in which the angle opens up. So when this angle opens up, of course, this opening of angle will create more angle strain. So here we have more angle strain. However, now the distance between the hydrogen atoms is 231 picometer, which is much more ideal because at that distance the two hydrogens can now safely stay in this arrangement. So there is less steric strain. So the combined sum is that although in this geometry there is more angle, but because it's less steric, so overall the B is more stable. So in energy calculations, we always look for what is the more stable arrangement. So now we can understand that the angles in all these molecules will be slightly more or slightly less than the ideal values of sp3 hybridization state, and that's all to reduce the strains caused by steric repulsions. By adopting the larger angle geometry in Eclipsed, the molecule becomes more stable, and this energy of stabilization is 5.6 kilojoules per mole. Apart from anti and eclipse conformation, butane molecule has a third major conformation, and this conformation is known as Gauche conformation. In this conformation, the molecule adopts a geometry in which the methyl group connected to number 2 is in the middle of the two groups or atoms connected to number 3, but they are not at the anti position. So let me explain with the help of a Newman projection. So let's start with the Newman projection at eclipse position. So at eclipse position, the groups connected to number 2 carbon, and I'll use blue color to represent the groups connected to the rear ones. So this is the eclipsed conformation of butane. So if we rotate to 180 degree, we get the extreme end of the conformation, and we call that conformation anti. So in anti conformation, the methyl groups are at 180 degrees apart. The dihedral angle between the two methyl groups is 180 degrees. Now, the conformation eclipse cannot go to anti-conformation directly, so it has to pass through many other conformations. So if this rotates by 60 degree only, then it will adopt a geometry in which the rear methyl group is in the middle of the front methyl group and hydrogen atom. This is relatively stable. It is stable than eclipse, right? So this geometry is known as Gauche conformation. If it rotates by another 60 degree, it will adopt a geometry in which the rear methyl group is now at 0 dihedral angle with a hydrogen. So this one, although the metal are not at the same position, but it is still known as eclipsed. So this is also eclipsed. It's again unstable, but not as unstable as the first eclipse. A rotation of 60 more degrees will bring this molecule to anti. It must be noted that in case of butane, the difference in energy between the total eclipse shown in number 1 state or 1 conformation and the total anti as shown here, let's call this number 2, is much larger than the ethane conformations. So therefore butane molecules would prefer to stay in anti-conformation as compared to the eclipse conformation. It has been calculated that at 20 degrees Celsius, about 70% of butane molecules stay in anti-conformation, and only 30% of butane molecules are either in eclipse or Gauche conformation. This figure shows us the energy of conformations of butane as a function of dihedral angle. As we can see that if the angle is 0 degrees, so that's the most unstable eclipse conformation in which the methyl group is right behind each other. So this conformation has maximum strain, hence it has maximum energy also. And the rotation about carbon-carbon single bond of 60 degrees will bring this to a Gauche conformation. It's relatively stable than eclipse, and a further rotation about 60 degree will again make this conformation to eclipse again, but however in this case methyl and hydrogen groups are eclipsed to each other, not methyl-methyl. Remember, methyl-methyl eclipse is the most unstable. So in this case the eclipsing is between methyl and hydrogen, which is again unstable but not as much unstable as the methyl-methyl eclipsed. And if the molecule rotates 60 more degrees, it will adopt the most stable conformation, which is anti-conformation. In anti-conformation, the methyl groups are at 180 degrees dihedral angle to each other. This is the most stable. So if we consider anti energy to be 0 and calculate the energies of other conformation with respect to anti, we can find that the methyl-methyl eclipse is 21 kilojoules per mole higher than the anti, and the Gauche conformations are only 3.8 kilojoules higher than the anti. The methyl hydrogen eclipsed conformation is 14.6 kilojoules per mole higher in energy as compared to anti. Further rotation of 60 degree again will increase the energy and molecule will adopt again methyl hydrogen eclipse, and then another 60 degree rotation will bring the molecule to Gauche conformation, and finally another 60 degree rotation will bring the molecule back up to the methyl-methyl eclipse position. Now we will discuss the conformations of few of cyclic alkanes or cycloalkanes. The smallest cycloalkane which exists in nature is cyclopropane. Now, because cyclopropane is a 3-carbon ring structure and the observed angle in cyclopropane is 60 degrees. So this angle is 60 degrees. Now, this 60 degree angle is considerably smaller than the optimum 109.5 degree angle, which should be the case because all carbons are sp3 hybridized. Because of this reason, this molecule is under a lot of angle strain. Furthermore, because cyclopropane, and it's true for other cycloalkanes also, uh, all carbons are connected to each other and they are present in as a ring structure. So therefore, the rotation about the carbon-carbon axis is not possible. Because if it rotates about the carbon-carbon axis, the other bonds needs to break, and which cannot happen. So therefore, in cycloalkanes, carbon-carbon bonds do not rotate freely. Now, because of this reason, uh, the 6 pairs of CH bonds, uh, this one and this one, so they have a zero dihedral angle. Similarly, this one will also have a zero dihedral angle, and this one, and then this one, and this one. So this molecule will also have a excessive amount of torsional strain also, because dihedral angle between all CH or carbon hydrogen bonds is 0 degree, and the total strain energy calculated to be about 116 kilojoules per mole, and this is considerably high amount of strain energy in cyclopropane molecule. Because of this reason, cyclopropane is a not very stable molecule, and this molecule undergoes several ring opening reactions which are not seen with larger cycloalkane molecules. In case of cyclobutane, we have a 4-carbon ring structure. Therefore, the observed angle between carbon is about 90 degree. Now 90 degree is also much less than the ideal 109.5 degree angle. So therefore, this cyclobutane is also experiences a considerable amount of angle strain. However, in planar form, again, the carbon and hydrogen bonds have zero dihedral angle, so therefore they result in a large torsional strain because of zero dihedral angle. So molecules such as cyclobutane and larger cycloalkanes undergo a slight change in their geometry, and that change will allow them to get rid of this torsional strain, or so that change is such that the ring adopts a slightly deformed structure. For example, if a planar ring is this way, so one of the corner of the ring will go up, two of the corner will go up and the other two will move down, and they will adopt slightly crooked ring structure, like we are folding a plane, like a paper. So this is known as a puckered or butterfly conformation. So when the molecule is in puckered conformation, then the dihedral angle is no longer 0. So they are not directly next to each other. So after adopting the puckered conformation, the torsional strain is reduced. Another thing to consider here is that after the cyclobutane molecule adopts the puckered conformation, this angle now, this one is not 90, it's less than 90, and it has been found that the angle in cyclobutane in puckered conformation is about 88 degrees. Now, reduction of carbon-carbon and carbon angle will result in more angle strain. But however, because adopting puckered geometry or conformation reduces the torsional strain, so this additional angle strain is uh, is not that is not that that harmful, or it doesn't produce any additional unstabilization of the molecule. In case of cyclobutane, again, the total strain energy is calculated to be about 110 kilojoules, which is still considerably high amount of energy. And because of this, cyclobutane is also relatively unstable molecule. Cyclopentane is one of the most common cycloalkane molecule. If cyclopentane adopts a perfect pentagon planar geometry, such as this way, then the angle, all the carbon-carbon angles will be 108 degree. Now 108 degree is almost perfect because ideally the angles should be 109.5 degree. So this gives cyclopentane quite an advantage when it adopts this conformation, because now it can have a minimum amount of angle strain. However, there is a another issue, and that issue is torsional strain. If cyclopentane adopts the perfect flat planar conformation, all CH bonds will be in will have the zero dihedral angle, and that will generate extensive amount of torsional strain. So therefore, the planar cyclopentane conformation is not very stable conformation. In cyclopentane, there are 10 CH bonds, so resulting in 10 torsional strain places. So therefore, cyclopentane will become extremely unstable. To relieve this extensive amount of torsional strain, cyclopentane adopts a geometry or conformation which is known as envelope conformation. So in envelope conformation, one of the carbon atom comes out of the plane, just like we open an envelope. So rest of the four molecules rest of the four carbon atoms are in the plane, and one of the carbon atom is above the plane. So this kind of conformation is known as envelope conformation of cyclopentane. The ball and stick model of cyclopentane in purely cyclic planar form is represented here, and as we can see that all these carbon hydrogens have zero dihedral angle in this conformation, which will result in extensive amount of angle strain. So therefore, the preferred geometry is, or preferred conformation is, where one of the carbon is out of the plane. So now the hydrogens of this out of plane are no longer at zero dihedral angle, so this will reduce the amount of torsional strain. So in envelope conformation, four carbon atoms are in plane and the fifth bends out of the plane. Cyclopentane exists as a dynamic equilibrium of five equivalent envelope conformations because it has five carbon atoms. And in all these five equivalent conformations, each carbon atom alternates as out of plane atom. So in envelope conformation, the average carbon-carbon angle is found to be 105 degrees. And in this envelope conformation, the number of eclipsed carbon-hydrogen interaction is also reduced. It's not zero, but it is less than the uh, purely flat planar conformation. So therefore, we can consider envelope conformation as an energetic compromise which balances a decreased torsional strain with increased angle strain. Yes, of course, the angle strain is a little bit more, but the torsional strain is a little bit less. The strain energy in cyclopentane molecule is found to be 42 kilojoules per mole, which is not that bad. It's not that high. Let's discuss the conformation of one of the most important cyclic alkane, which is cycloalkane. If cycloalkane adopts a pure planar geometry, such as a regular hexagon, the angles will be 120 degree, which would cause a considerable strain, angle strain. And needless to say that cycloalkane is not present as a regular hexagon, although we do show in the line structure formula as a regular hexagon. So cyclohexagon is not it does not adopt a hexagon geometry. Instead, cyclohexane adopts different kind of puckered ring conformations, and all these puckered ring conformations are convertible via carbon-carbon rotations. The most stable of the puckered ring conformation of cyclohexane is chair conformation. And the side view of chair conformation is shown here, and it's extremely easy to visualize what's the meaning of chair conformation. So let's imagine that we have a flat planar hexagon. If one side of the hexagon, one edge of the hexagon moves above the plane, okay, so these 4 carbons remain in the plane and this one carbon is above the plane, and the other carbon, this one, moves down the plane. So therefore this is down the plane. So this conformation is known as chair conformation. Why chair conformation? Is because it kind of looks like chair. So that's why it's called chair conformation. So the top view of chair conformation still would look like a regular hexagon, but we know that it's not the regular hexagon. In chair conformation, the bond angle is 110.9 degree. So all bond angles are 110.9 degree, which is quite close to the optimum bond angle of 109.5. So therefore it has a minimum amount of angle strain. Another important thing to notice here is that in chair conformation, all CH bonds are at staggered position to the neighboring CH bond. So for example, so this CH bond, this one, is at staggered position to the neighboring one, and it's also staggered to the next neighboring one. So because of this, the torsional strain is minimum because dihedral angles are always 60 degrees. Another important thing to remember here is that in the chair conformation of cyclohexane, we have 12 hydrogen atoms. Out of those 12 hydrogen atoms, 6 of them are in axial position and 6 of them are in equatorial position. Let me explain what are axial and what are equatorial. Axial positions are those hydrogens which are perpendicular to the plane of the carbon atom. So for example, if this is the molecule, imagine that the carbon atoms are roughly in this plane. So all the hydrogens which are perpendicular, for example, this one, this one, this one, now 3 above and 3 below the plane. So these 6 are called axial hydrogens. And the remaining 6 are equatorial hydrogens. So the equatorial hydrogens will be the remaining ones. So this one, this one. In other words, the hydrogens, sorry, let me use the same color. 6 hydrogens above the plane and 6 below are axial position. Each carbon has one axial and one equatorial. The remaining hydrogens will be equatorial. So these are equatorial. A representation of axial and equatorial hydrogens are shown in this figure. If we imagine the plane of carbon atoms as represented here, then the hydrogens which are above the plane and below the plane, represented by blue spheres or blue hydrogens, are called axial, and the hydrogens which are parallel, roughly parallel to the plane, are called equatorial. It is an extremely important skill to draw the conformations of cyclohexane and identify the axial and equatorial hydrogens. In this slide, I will explain the method to draw the conformation and how to label the axial and equatorial position. So in order to draw a chair conformation of cyclohexane, you must draw two parallel lines, and one line should be slightly uh, 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 it should be slightly drifted from the other one. So these two are parallel lines, and then draw another line here, and parallel to that line draw a line here, and then connect this line with carbon atom here and connect this one here. So this is a chair conformation of cyclohexane. Now if you want to now draw the axial hydrogen, so you can start from either corner. So it could be either at this corner or this corner, doesn't matter which corner you are starting at. So and we can already see the carbon number 1. I'm going to label it, so it's 1, 2, 3, 4 and 5, 6. We can already see carbon number 1 is above the plane. If this is the plane, carbon 1 is above the plane and carbon number 4 is below the plane. So if you start the carbon which is above the plane, then the axial position is kind of like a flagpole straight up. So this would be the axial position. And then move from carbon 1 to the carbon 2, just draw another flag but in the opposite direction. So if carbon 1 is above the plane, so carbon 2 will be below the plane. And carbon 3 will be above the plane. Carbon 4 will be below the plane. Carbon 5 will be above the plane, and carbon 6 will be below the plane. So these 6 hydrogens are axial hydrogens. And these 6 positions are known as axial positions. Now, how to draw the equatorial position? So it's as simple as that. So now remember, all carbons are tetrahedral because they are sp3. So we just need to complete the tetrahedron now. So therefore, if axial position at number 1 carbon is flagpole kind of above, just complete the tetrahedral position. So this would be the equatorial position. The yellow one is equatorial. Similarly, the equatorial position here will be this one. Equatorial position here will be this one. So the yellow ones are equatorial position. So let me clean up my structure. You can clearly see what are axial, what are equatorial. Another thing you must remember is that the chair conformation goes from one chair to another chair. Let me explain what I mean by that. What happens here is, now in the structure shown here, number 1 carbon is above the plane and number 4 is below the plane. So when the chair flips, this carbon moves down and this carbon moves up. So we can draw it again the same way. So now number 4 carbon is above the plane, number 1 is below. One thing to remember is that when the chair flips, the positions which were axial in one side, they will now become equatorial in the other chair. So therefore, we'll see that the purple hydrogens were axial on the left hand side. Now the purple hydrogens will become equatorial. So instead, the yellow ones will be now axial hydrogens. Extremely important concept. And the purples will become equatorial. Both of these chair conformations are equivalent, and cyclohexane molecules is in equilibrium with both the chair conformations. This figure represents the ball and stick model of 2 chair forms, and in the left hand side conformation, the blue spheres or blue hydrogens are axial positions and the red ones are equatorial. Remember, the axial positions are those hydrogens which are perpendicular to the imaginary plane of the molecule, and the equatorial are those which are parallel or within the plane of the molecule. So as you can see that when the chair flips, the axial position becomes equatorial and equatorial becomes axial. So now we know what is the chair conformation of cyclohexane. Let's talk about another important conformation of cyclohexane, and it is known as boat conformation. In boat conformation, both carbon number 1 and carbon number 4, so that would be 1, 2, 3, and 4, both of these will come out of the plane, but they will move towards each other. In chair conformation, one goes below the plane, the other one is above the plane, but in boat conformation, both of these move in the same direction. So cyclohexane will adopt a geometry or a conformation which looks like a boat, and hence it's called boat conformation. A boat conformation is considerably less stable than the chair conformation because of the torsional strain. As you can see that all the carbon hydrogens are now within the same plane, so the dihedral angle is 0. So therefore boat conformation has a excessive amount of torsional strain. The other instability factor is due to the presence of these two hydrogens at this position, this one and this one. So these two hydrogens, they cause steric strain, and this strain is known as flagpole interaction. The difference in energy between chair and boat conformation is approximately 27 kilojoules per mole. Some of the strain in the boat conformation can be relieved by a slight twisting of the ring to a new conformation, also known as twist boat conformation. As you can see here, that the ring is slightly twisted. In doing so, the torsional strain is relieved because now the dihedral angle is not zero anymore. It has been calculated by molecular modeling computer program calculations that approximately 6.3 kilojoules of energy is saved, or in other words, a twist boat conformation is 6.3 kilojoules per mole more stable than the boat conformation. One thing to be noted here is that although there is a energy barrier, or in other words, the boat conformation is less stable than the chair conformation, and in order to go from chair to boat, there we need energy, or in other words, there's an energy barrier. Still, molecules of cyclohexane, they interconvert between all these conformations. For example, if a molecule starts with a chair conformation, something like that, so that's a chair. If this molecule, this carbon atom goes up, so this chair conformation will adopt a boat conformation now, and of course we're gonna need some energy because there will be energy barrier, and from here boat conformation, if this goes down, it will go to the second chair conformation. So in other words, whenever a chair conformation flips from one chair conformation to the other one, that transition undergoes, or that transition goes through the boat conformation. So that's the energy barrier from going from one chair to another chair. The energy diagram for the interconversion of chair, twist boat, and boat conformations of cyclohexane is shown here, and as we can see that the chair conformations are most stable, and in order to go from chair to the boat, there's a huge relatively large energy barrier of 41.8 kilojoules, and then twist boat is slightly stable as compared to pure boat, and then from pure boat molecule undergoes conformation to become twist boat, and from twist boat it goes through the same energy barrier, and then it forms the second conformation of chair. In case of cyclohexane, the two chair forms are equivalent. That means is that whenever we have a cyclohexane molecule, there is an equal chance that, or 50% of the molecules will be in this formation where 1 is above the plane and number 4 is below, and 50% is when 1 is below the plane and 4 is above the plane. However, whenever we have a substituted methyl cyclohexane compound, whenever we have a substituted cyclohexane such as methyl cyclohexane, then this equilibrium is not same. for example, instead of regular hexane, so that this is the regular hexane, if we have a methyl cyclohexane, in that case we have again two possibilities. One possibility is and the other possibility is, as you remember, the bond in which is perpendicular to the plane, such as this one, so this is axial, and when the chair flips, we remember that the axial bonds become equatorial, so CH3 here will be at equatorial position and not axial anymore. Whenever we have a bulky group and at any position, it will prefer to have a chair conformation in which the bulky group is at equatorial position. So therefore the equilibrium will be largely shifted to the left and not to the right. There are hydrogen atoms also connected here which are not represented, so those are there, please remember. So in other words, the large bulky group is preferred over the equatorial position. So the chair conformation, one of the chair conformation in which the group adopts the conformation where methyl is at equatorial, that one will be preferred. Why it's preferred? Because if a bulky group is at axial position, that axial position has steric interactions with the hydrogen atoms at the number 3 and 5. So for example, this is number 1 carbon, that's number 2, this is number 3, this is 4 and 5. So these interactions are known as 1,3 diaxial interactions. So these diaxial interactions make the large methyl group at axial positions unstable. So this is not preferred. So therefore it adopts the other chair geometry in which the methyl group is at equatorial position and now is far away from those interactions. So diaxial interactions do not exist in this conformation.